It's so interesting.
It's so interesting.
It's so interesting.
It's interesting. It's so interesting.
Okay. Welcome to It's So Interesting, where people talk about their work and life experience. I am George Spitzer. Today I have with me Jonathan Essen, a theoretical physicist. Let's get right to it. Make sure I understand. How do you define a theoretical physicist as opposed to a, regular physicist?
I would say that there are sort of two branches of physics. One is theoretical physics, which is the area that I've been trained in. Attempt to describe the material world using mathematics. And the other side of physics is experimental physics. And then there, as far as a theoretical physicist is concerned, what you do as an experimental physicist is check whether or not the theoretical physicists are right. Well, mostly what they do is prove that theoretical physicists are wrong about something and that something has to change.
It starts first with the theory, which you come up with, and then the practical physicists convert it to reality.
Theoretical physicists like to think that way. But the other side of the coin is most theory is inspired by results that were not anticipated, and that experimental physicists come up with.
When you start working, I assume a lot of it's based on math, and theories are based on math?
Yeah, theoretical physicists invent new math all the time, that mathematicians have to figure out what it means sometimes. But physicists are happy if it works, and they're not always concerned about whether or not things are rigorously defined from an axiomatic, mathematical, rational construct. You know, they're happy just if the calculations come out right a lot of times.
In other words, when you do 2 plus 2, you do get 4, not 2.
Yeah, that we demand that works. Yeah.
I don't know which way to attack some of my questions, so I'm going to start off with a general one. Given that you are a theoretical physicist, much of which is based on math and possibly unproven theories, what would your view be of the world as we know it? Do you think it's a mathematical construct, more of something that comes out of our fertile imaginations, or is there some physics involved, something physical, and would that physical thing be the hard time, like the kind you can knock on wood, or could it be even as substantial as the concept of metaphysics?
I think theoretical physicists have all kinds of different opinions about the answer to this question, and I'd be happy to tell you mine.
That's why we're together, so
Okay.
Tell me yours.
I think that the material world emerges out of something which is utterly unknown, which is this thing we label with the word awareness, but which we have no way to really examine. For me, physics is more of just an adventure of enriching our sense of awareness. Physicists has discovered all kinds of amazing things that you never ever would have expected just based on your 5 senses.
Okay, there you go. You just gave me a door to open for you. Give me some examples of what you're talking about. Things discovered that we would not be aware of.
The last 150 years, I think, unexpected things coming out. Some things that come to mind are quantum mechanics is a non-intuitive description of our experience. There's also, even without quantum mechanics, you still get all kinds of weird things.
We need to get specific here.
Okay.
You've mentioned quantum mechanics twice. What is quantum mechanics?
To a theorist, is a mathematical construct in which you put in some details about the situation you're trying to understand, and you do some calculations, you make some approximations, and out comes an answer, which happens to agree in every case we've ever looked at with what the experimentalists come out with. But what people think is so weird about quantum mechanics is the way that this mathematical construct works. It doesn't work the way that you might sort of assume that the world works.
Tell me.
Well, okay. Something that happens in quantum mechanics is you lose the concept of particle. Well, you have particles, but they don't. They behave like waves as well. Well, I think the Greeks probably were the first people to come up with the idea of a particle, a unit of matter which can't be divided any further without changing it. For a long time, people thought of atoms as some very, very small piece of matter that you could, if you looked closely enough, it would look like a little billiard ball or something like that. So for a long time, people thought, if you zoomed in far enough, you'd end up with a little ball, and they'd bounce around and bang into each other, just like billiard balls do, on a billiard table, right? Mm-hmm. But in quantum mechanics, they don't do that. They do something else. It's hard because quantum mechanics is a mathematical thing, and it doesn't really naturally live in the English language.
Well, that's why we're here. We need to translate. I mean, you're at a cocktail party and someone says, "What do you do?" And you say, "Well, I'm a theoretical physicist. I'm digging into quantum mechanics." They go, "Oh, really? What is that?" You need to tell them in about 2 minutes.
Well, okay, this thing. Okay, maybe I'll just cite an example instead of trying to explain.
We're not talking. Graduate courses here. We're talking about just regular folks like me understanding what you're talking about.
There are certain experiments that you can do where that whole framework just doesn't correspond to what we measure, and so something else is going on. One example of this something else that pops up is it's called the uncertainty principle in quantum mechanics. That principle says that if I have a piece of matter, something with mass, sitting there, I can measure where it is, and I could also measure its velocity, its speed, and direction. So I could say, what direction is it going in, and how fast is it going. But if I try to measure both the position and the speed, maybe I measure the position, and then I measure the speed, but the moment I measure the speed, whatever information I had about the position is destroyed.
It's out of date.
They're just not compatible things to know at the same time. You just can't know both.
Is that where quantum gets in?
Oftentimes that's cited as an example of why quantum mechanics is weird. What started as a billiard ball ends up as being kind of smeared out. Maybe if I measure exactly where it is, I don't know where it's going. So now it's
you don't know where it's going. You don't know what the velocity is.
Yeah, where is it going to be in a nanosecond? I have no idea because but I do know exactly where it is right now.
So how does it have any practical use in theory?
I don't care about exactly where it is. I only care about approximately where it is. And if I know that, then I can have some information about where it's going as well. So in quantum mechanics, you start to deal with that kind of an object. A smeared out thing and not billiard ball.
A more or less billiard ball.
Yeah.
I'm going to go back to a question I asked earlier. What is your perception and theory as a theoretical physicist of the material world as defined by matter?
The world around us, we only see it because of these things we call forces. Mid-20th century, or maybe the early 20th century as well, people were interested in radioactivity. Where does that come from? And eventually it was found out that it comes from splitting of nuclei, of atoms, and changing atoms into other atoms. And on the way, what comes out are all kinds of different particles, like a whole zoo of particles comes out. A lot of work was done in the 20th century trying to understand all these different things that come out of what happens when you split up a nucleus into small pieces. You end up with, I think in the 70s there was probably a paper published every week or every month with a new particle being discovered. And then the question is, where did all these come from, and how are these all related to each other, and how do these interact with each other? And that was actually nailed down pretty well. One of the biggest triumphs, I would say, in the 20th century was what they ended up with was this thing that got named the Standard Model, and it explains all the properties of all the different particles that we've seen.
And I would like to understand what a theoretical physicist would think of the concept of nothing. Is there such a thing as nothing?
That is an interesting question. That is one that has not been nailed down very well. The word you say, nothing, corresponds loosely with the word vacuum in physics. But the vacuum is not nothing.
You're sounding like a theoretical physicist right there. Okay. Curious to know if nothing is nothing or not nothing.
Okay, so...
or nothing not.
As far as a physicist is concerned, they're just happy to discover something new, and that's just exciting. But there are times when those discoveries can have all kinds of unpredictable effects on the world. And so you can ask the question, is it moral to discover something that could end up, hurting people? But on the other hand, maybe your discovery could end up helping a lot of people. I got a good example. And he was working for a long time designing what is the optimal way to place bombs in a city to cause the maximum destruction, right? We don't want the bombs to land on top of each other because then we've bombed what was already bombed. We want to bomb something new. So we'd like to spread the bombs out so that they destroy as much as possible. We don't want them to be too spread out, right? Because we just want to bomb, this one city. and we don't want them to be too close together, otherwise we're not destroying enough, right? And so we worked out an algorithm, and it ended up, it was fine. It's a well-understood field now. But then he was asked by another part of the war effort to design, well, where should we place hospitals in for soldiers in the field, so that each hospital can help the most number of soldiers. And it turns out it's the exact same answer as, where do I put the bombs? I just want to cover the most area, and I don't want to cover the same area twice. It's the same answer to two very, you might think, different questions.
But discovering that principle can be applied and overlaid on many other disciplines now. So it's a major discovery.
All kinds of consequences have come out of that one idea, which some are good, some are bad.
And as with all discoveries, they weren't invented per se. That principle always existed. It's just that no one knew it.
Yeah, I would say that.
How did you discover that, or do you remember a moment in your life, particularly when you were a kid, that you realized you wanted to be a theoretical physicist? I mean, this is pretty arcane stuff.
Well, actually, I was not a very good student for most of my childhood. I mean, I was a smart guy, and I liked learning things about science and things like that, but I used to have a lot of problems with math. In ninth grade, I started to get it, and I remember a moment in which I started to get it.
Tell me about that moment. Was that because of a teacher, or just something you discovered on your own?
Well, it was on my own. I was taking a test, and I'd always check my work when I was done with the test. And I'd end up finishing the test with lots of time, and so I'd check my answers, and I'd turn it in, and I still wouldn't get very good grades on it. And so I remember sitting there with this test, and I checked, and I had finished it early, and I checked over all my answers, and I said, looks good, let's turn it in. And then I said, wait. And I just realized that all this time I'd been checking my answers, I had been checking that they were right. I hadn't been asking myself, could this be wrong? And so I looked over the test again, and I found that there were 3 questions I'd answered incorrectly.
So there's your budding theoretical physicist.
You know, it's a little bit unpleasant, right, to say, I could be wrong, and let's figure out if I'm wrong. Like, seriously, let's get into this. But yet, you get to correct yourself. For me, it's just cool that you might be wrong, and you can figure it out.
I've asked this question of others, and this one's a stretch. We'll just see where we go. In condensed matter theory, which is your specialty, again, you can't in advance say what you're going to discover, otherwise it wouldn't be a discovery. At the same time, what are your hopes, expectations in that area?
I worked on a project within condensed matter theory, which would be really exciting if it were to if people were to make progress on it.
Well, tell me about it.
Okay. We're going to get into some more words, though.
That's fine. The words will help us get to a concept, because I don't want to stumble over words at this point.
Okay. Yeah, it would be really exciting if they could work out how to build something called a quantum computer. The easy word, which is computer. You give it some data. The computer then applies various operations to the data. For example, maybe it sends your email. But there are other things it could do, like maybe you give it some numbers and it adds them all together. And a quantum computer does that. It's just that the way that it changes the data is different from a normal computer in terms of what you can do to the data. And it turns out that you can answer some questions on a quantum computer much more easily than on a normal computer. Let's call it a digital computer. The one thing people want quantum computers for, and the one thing that they're paying lots and lots of money for people to research into quantum computers for, is they would like to know how to break certain encryption algorithms. So when you log on to, Amazon.com, buy a book, you are relying, and you give them your credit card information, you are relying on Amazon.com to keep that safe and not to let somebody know what you gave them. But it turns out that a quantum computer could figure it out really easily. 100 years of computing time on a digital computer to figure out what information you gave to Amazon.com, but a quantum computer could maybe do it in a few seconds. Problem is, nobody knows how to build a quantum computer, and there are all kinds of different ideas about how to do it. I spent about a year working on one idea of how to build one of these quantum computers. The problem people are trying to address when they're building quantum computers is that once you give the computer some data, it just turns out that quantum computers are just really, really sensitive to errors. My research was is it possible to build a quantum computer which is not sensitive to some of these errors? And so it turns out that it might be possible, still quite a ways off.
Well, thank you very much for being with us. I've been speaking with Jonathan Essen, a theoretical physicist. If you'd like to hear this show again, go to itssointeresting.com. Click on his show or those of others that we've interviewed.
It's so interesting.
It's so interesting.
So
It's so
interesting.
interesting.
It's interesting.